So great, so let's get started. So welcome back, everyone. So first, just a quick announcement. So there's a data science club, if you're not aware. So it's pretty informal. It's run by some students. It's meant for people with data science backgrounds of like all levels. There's other cool data science activities going on. So at the U, there's a there's a data science seminar every Friday at 2 that I help run. The data science seminar is meant to be fairly accessible, but it's kind of a little bit more geared towards graduate level research. And this data science club is not designed just for kind of graduate level sort of stuff. So if you're interested and you just want to kind of learn and get to know kind of what's going on with data science, this is a friendly club to join. The first social will be Monday, September 13th. There's some stuff I've been helping the planning on this. There might be some data set that they kind of just throughout the semester just kind of practice looking at and trying some techniques out on. But it's not something you need a lot of background to get started in. If you're in this class, you should be in great shape. Great. So we are moving past the review section. We're going to go over Bayes' rule, which you've probably seen before in your probability course. But we're not just going to just look at Bayes' rule, just a definition. We're going to actually get to start to do some small amount of analysis today, right? So this is the first day we get to, so we're going to see how to actually build a model using Bayes' rule. And so this lecture and the next one will kind of go through the ways how to do that. We're going to go through a kind of an example at the end of today's lecture, and then kind of go through a more complicated version at the start of next lecture. And this will be building a very simple, continuous model of trying to kind of, model is going to be like a single point. Okay, so it's kind of the simplest version of this, like a single value with Gaussian noise. So this analysis we'll be able to work through it from first principles, and it's going to kind of be the basic framework used in like almost the entire semester. Okay, a very simple example, maybe kind of too simple to think we're actually building a model, but you'll see that the same sort of thing we're doing now is going to kind of be repeated through more complicated models throughout the semester. So, okay, great. So Bayes' rule. This is so Bayes' rule, and the apostrophe comes after. In case you're wondering, the apostrophe comes after the S. So it's named after Thomas Bayes, whose name, it's like mine, ends in an S. So if you put the apostrophe after the S, okay. And so this is a rule about conditional probability. So I'm going to have two events. Okay, I'm going to call them M and D, and we'll see why I call them M and D. and it's a kind of a property about conditional probability of M given D, right? And it's a way of rewriting this, and it's simply probability of D given M times the probability of M divided by the probability of D. Okay. All right. So it's just a rule about conditional probability. Kind of, and the way I suggest you think about this, the way I do, is that M is going to stand for like a model, and D is going to stand for the data. Okay. And what we would like to do is say we have a bunch of models that we think might be the thing that represents the data. Okay, might be the best way to represent the data. And we're so given some data. We've gone and so we've observed some data. This is what we do in this class. We'll be talking about how do we build models after we've observed some data. We want to find the one that has the highest probability of being the right model. Okay, so that's what this left hand is saying. Left-hand side is saying we want to kind of observe some data, D, right? And then now that data is so given to us, right? So given that data, conditioned on that data, what's the most likely model? Okay, and then there's something on the right-hand side, and that right-hand side looks more complicated, right? I would just like to calculate the probability of the model given the data. Why don't I just calculate that? Well, it turns out that even though this right-hand side is more complicated, it's going to be so much easier to work with. Okay, it's going to be has another conditional probability that looks basically the same probability of data. So given the model, turns out that's going to be something. This term over here is going to be kind of the root of the calculations, most of the calculations we're going to do. This is something we'll be able to write down a formula for. Okay, this is the probability of the data. So given the model, this one is, we'll talk about, is often called like the likelihood. And then there's the probability of the model. This is another term here. Okay, so this one, the probability of the model is often called the prior, and the probability of the data given the model is often called the likelihood. Okay. Okay, so we'll often be able to write down formulas for the likelihood. Probably the prior, probably the model is something we're sometimes going to be given. In some cases, we're going to be given, and then we need to use this formula. The probability of the data, this term here on the bottom, okay, this term here on the bottom, turns out it's so not very important. This is typically something that's not very important. So we sometimes will be able to calculate it, but we'll often just ignore this term, and we'll see why we can just ignore this term. Okay. So okay, but before I go through some examples, let me first say that this is, so it's just a formula. You can derive it from the definition of conditional probability, right? So if I know by the definition that the probability of the model and the data is equal to the probability of the model given the data times the probability of the data. All right, so this is true because I could have, by the definition of conditional probability of the model given the data, I could have moved this term here over onto this side. I can divide through by the probability of the data and the probability of the data, right? So if I divide through it on both sides, then that's just the definition of the probability of the model, so given the data, okay? So, and so we also have that the probability of the model given, probability of the model and the data is equal to the probability of the data and the model both being true, right? There's a symmetric operation. And this is then is equal to, by the same argument, the probability of the data given the model times the probability of the model. Okay, so now I have the probability of the model and the data is true to both of these things. Okay, okay, so now the probability, I can now solve for, I can solve for this term. Okay, and this will be equal to the probability of the data given the model from the right-hand side of the bottom expression times the probability of the model divided by the probability of the data. Okay, so and this is Bayes' rule right here. Okay, so this is just a property of, you know, that you can write down from conditional probability. Okay, you may have heard of, there's sometimes this this controversy between a frequentist versus like a Bayesian view of the world. Okay, it is not a controversy about this formula itself, about the truth of Bayes' rule. It's controversy about how to do the analysis, what to value inside the analysis. Okay, so for this lecture and kind of especially the next lecture, we'll kind of take a Bayesian view of things, but frankly, most of the, and we'll use this to kind of derive how we're gonna set up a bunch of the cost functions, but most of the class will be closer to what would be considered like the frequentist view. Frequentist view often involves like classical hypothesis testing. We are not going to get into hypothesis testing, however. We're going to look at kind of the most likely estimator, but not all of the modeling, all the uncertainty associated with these things. And that's what is kind of often associated with this Bayesian view of the world. So, okay, so the point is Bayes' rule is just a formula, and this formula is just kind of true. I will expect you kind of guys, everyone to understand, to be able to reproduce so Bayes' rule. Okay, so in the rest of this lecture, we're going to kind of see some examples and show how to use it to do some data analysis. Okay, so the foundation of it, if you just think of it as a formula, it might be hard to remember what's going on. But if you think about it as, think about like the probability of the model given the data, I'd like to find the most likely model given what I know about the data, and I can calculate the likelihood and I can calculate the prior, well, then it's going to make sense. It should be something you should be able to remember. So, okay, let's start with simple example here, just the calculations here. Okay, so I'm going to start with the simple two events and like a table, m equals 1, m equals 0, right? And I have d equals 1 and d equals 0. Okay, and this is a probability table. So let's say 25% the model and the data are true. 50% of the time the data is true, but so not the model. 20% of the time the model is true, but not the data, and 0.05. Okay, so we'll be assuming the data is true. We'll be conditioning on the true, but we need to write this down in order to do the calculations here. Okay, and so I just want to calculate both, so both sides of the formula, right? Both ways of seeing this expression. This is probably the model, so given that the data is true, And so one useful reason I'm going to write out this way is in these probability tables, you often have like treat it as a binary variable. It's true or it's not true. This is kind of an event. And then in the probability, we just write the model and the data. This implies this is the equals 1 case. Okay, so if you're wondering where the equals 1 equals 0 goes, it's shorthand. You just write it that way, then it's that means it's the equals 1 case. It's true. Okay, and then so the simple way of calculating this is the model and the data is true divided, or the model and the data divided by the probability of the data, right? And the model and the data is going to be 0.25, right? That's the upper left corner there, and the probability of the data, that's going to be the sum of the two cases here. That's going to be 0. That's the marginal probability of the data. That's 0.75, and I get 1/3. Okay, and now we're just going to check that this is true based on the using. So that's the calculation of the model given data from the table. Let's do this now using Bayes' rule. The data given the model times the probability of the model divided by the probability of the data. So the first thing I need to do, well, I need to calculate this other conditional probability here. The conditional probability, this is going to be equal to, that's the probability of D intersect M divided by the probability of M, and then I'm multiplying this by the probability of M, the probability of D. Okay, well, the M's are gonna, I don't need to cancel them yet. Let's see, then this is gonna be probability of the data and the model, again, is 0.25 times the probability of the model being true. This is gonna be 0.45 divided by 0.45, which is again the probability of the model, times the probability of the data, which is 0.75. And because these guys cancel, I'm going to get back the same thing as before. Okay, great. So if I do this, everything checks out. I just want to kind of confirm that. Okay, so it's clear what's going on here. The Bayes rule version looks more complicated. Okay, so what's going on? Why is this useful? But any questions? This is all clear. Yeah.
Where did you get the 0.45?
Zero.
Is that given in the problem?
Yeah. So this is the marginal probability of the model,
Oh.
and this is 0.55. The same way I did the marginal probability of the data, 0.75, 0.25, right? Okay, great. Yeah, good. So good to ask questions if you're confused. This is kind of the trail end of the review, so great. Okay. Okay, good. So mechanically, this is how this all works. We're going to need to do this with like these probability density functions later, so it's good to make sure you understand it with the discrete random variables here. Okay. Let's see why this is interesting, and I'm going to call this is I'm going to call this the cracked windshield example. Okay. Okay. So I had when I was in graduate school, I had a car and the windshield kept cracking, and kind of I was interested in why was this windshield always so cracking in my car. It's one of these where it was a pretty upright thing, and anytime a rock hit it, just crack. So very annoying. So consider you bought a new. So this is going to kind of lead to this example. You consider you bought a car, and the windshield or the car came from. And I'm going to have an event W, and this is that the windshield was cracked. Is it I before E or E before I? I before E? Yeah, okay. Okay, the windshield was cracked, and I wanted to blame someone, okay? Maybe it's not good to take, to try and seek out blame, but I said there's some factory which installed or does, installed the windshield some way, and there are three factories, A, B, and C. Okay, and it would have come from one of these three factories, and I think the factory is to blame. Okay, so these are going to be the space of my models. Okay, so these are going to be the models here, and I'd say either the windshield's cracked because of factory A, factory B, or from factory C, and I want to know which one is most likely to have caused the problem. Okay. So the first thing I do is I look up and I say, well, the cars in my area, they come from different factories because they're most likely to come from the closer factory. But sometimes someone orders a kind of a car with a special feature, and they're making that in some other factory. So I find out that the probability of my car coming from a certain factory was as follows. Let's see, factory A was 0.5, factory B was 0.3, and factory C was 0.2. Okay, so something like 20% of the cars that would have come to me, I don't know which one it came from, but it would have come from factory C 20% of the time, factory B 30%, factory A 50% of the time. Okay, so I know this. I don't know for sure which factory my car came from, but I know of all the cars I could have gotten, this was the base probability. So this is my prior assumption on which factory the car came from and who is to blame for my windshield, perhaps. Okay, so and then I look up online. The kind of apparently this is a problem, and people have found out that the windshield cracking is somehow related to the factory that it came from. Right? There's different probabilities of having a cracked windshield given it came from a different factory. Okay, and so the probability that a windshield is cracked out of all the cars coming out of factory A. After a year, what fraction of them had cracked windshield? This one was 1%. Okay, so maybe these numbers are artificially high or something, but we'll use them as an example. Probability of having a windshield cracked out of factory B was 10%. This one seems problematic, and the probability of the windshield cracked out of factory C is now going to be 2%. Okay, so these are statistics of did the windshield crack after it, depending on which factory it came from. Okay, so now I would like to know which factory was most likely the one that made my car, given that I know my windshield cracked. Okay, and this is the only information I'm able to gather, so I'm trying to calculate this. Okay, so now I can put this all together. See, I can say the probability of A given the windshield crack, right? So the probability that my car came from factory A, given that my windshield was cracked, right? This is what I'd like to calculate. Well, I can use Bayes' rule now to say the probability the windshield cracked given the factory A divided by the probability of, so times the probability of factory A divided by the probability that the windshield cracked. Okay, and I can write this as 0.01. That's the probability that the windshield cracked given A times the probability it came from A, 0.5, divided by the probability that the windshield cracked. Okay, and so this is going to be 0.005 divided by probability correct. Okay, so I can write this down for the probability of A. I still have this annoying divided by the probability of the windshield cracked that that I'm dividing by, but we'll see this isn't going to be a huge problem. I can do the same thing with factory B. So again, probability windshield given B, probability B divided by probability W. This is now 0.1 times 0.3 times probability of W, and this is 0.03 divided by probability of W, okay? And I can do the same thing with C, okay? We'll skip to here. This is 0.02 times 0.2, which is 0.004. Okay, great. So I've calculated this now. And if you can't see this on YouTube because they put a big U over there for whatever reason, it's a 0.005 for A, 0.003 for B, and 0.004 for C. Okay, so now I want to find the most likely factor here. The most likely factor, well, I don't have the probabilities. I don't have the probabilities here. How can I tell the most likely factor to have produced my car that has a cracked windshield? Yeah.
They all have the same denominator.
Yeah, that's right. They all have the same denominator, so I can kind of ignore it, right? I can say, to find the one that's most likely, I just need to look at the numerator, and they're all divided by the same denominator here. So the most likely one is going to be factory B. That's almost 10 times as likely as the next as the other factors. Okay, maybe yeah. So this is a much more likely. It's about I could. Okay, so I could, and I'll leave this to an exercise for you. I could calculate the probability of W, right? In this discrete setting, I could do it. In general, we'll move on to the next stuff. I won't generally be able to calculate W, but in this case, I could calculate W. How would I calculate W? I know that there's only 3 factors, right? So what do I know about the properties of a probability? What are the 3 properties of a probability that they have to have? The first one is every probability needs to be between 0 and 1, right? Second one is that the probability of the total sample space, that I fall in the total sample space, which is A, B, and C, that has to be equal to 1 exactly. And this third thing is that if I have disjoint events and I add up the probabilities of those events, they have to equal the probability of the union of those events. Okay, what is the union of A, B, and C? The total sample space. Right? What's the probability of the total sample space? Yeah, it has to be 1, right? So I know that these 3 probabilities, 0.005 over probability W, 0.03 over probability W, and 0.004 divided by probability W, I add those up, has to equal to 1, so I can then solve for probability W. Okay? Okay, so you can figure this out here. In general, we'll have a space of models, which is an infinite space of models, and figuring out how to do this will not is non-trivial. Okay. Great. So, okay. So what I've done here is I wanted to find the most likely model, right? The best explanation for my data. My data is that the windshield was correct. Okay. We're going to be doing this now, but we're going to be using kind of other types of data, and we're going to be using kind of other spaces of models, which are going to be continuous spaces of models. Okay, but it's going to have the same sort of property going on here. Any questions I need to deal with, or?
Yeah, you might want to address it.
Okay, well, let me look in the chat here a sec. Okay, they all F21, great. What do the sample space they belong to? The sample space is the space of the models, right? So that I just define this A, B, and C. That's just this, it's just a discrete sample space. And then, yeah, great. Oh, okay, good. So the people in the chat got it. All right. You have to compete. The in-class people need to kind of step it up a bit. Okay, that's fine. Great. I know it's sometimes easier to like answer questions in the chat. Actually, that's something I found the last year or two. But you know, I think you all can hopefully do that here in class as well. So okay, great. So now we're gonna be looking at this again, this probability of model given the data. And we're going to looking at what's called a maximum, so posteriori estimate, often just called a map estimate. Okay, so this is kind of an example of what we just did in the previous problem, but we're going to talk about this more so generally. So I'm going to have I know my model is going to come from a space of a sample space of models. In the previous example, this was A, B, and C. That was it. But we're going to look at some more general things. And our goal is to, I want to find what's called M star, which is going to be the one which maximizes this probability. Okay, and often we want find something that optimizes some function. We're going to put a star on it, right? That's the one that optimizes it from some space. Okay, and so I'm going to write this down in this way: an arg max of M. I'm going to restrict it to be an element of this space of models. Okay, and I want to maximize the function M given D. Okay, so this argmax operator, okay, is something you may not have seen before. It has a set that I write underneath it. Okay, and I say M is going to be an element of a set. Okay, and I want to find the maximum value according to this function, right? Okay, so it's going to be a function here, and I want to find the maximum element from a set in the function. If I don't have the arg, I just take the max, this returns the maximum value of that element, but I'm going to return the argument that maximizes it. So that's the actual model. Okay, so that's what this argmax notation is saying, and it's an element of a set. Before the set was ABC, and I found that model B was the one that maximized this probability. Okay. And so I can rewrite this using Bayes' rule, okay, as model given here of the probability of the data given the model times the probability of the model divided by the probability of the data. Okay, this is just rewriting with Bayes' rule. And now I can do something. Now let me formalize this trick that we did in the last problem. This is also arg max of M, the space of the models, times the probability of the data given the model times the probability of the model. now I do not need to write this denominator, right? I don't need to write the denominator to find the argmax. I don't care about the value that maximizes it. I'm not asking for that. I'm asking for the model that maximizes it. And that's why I can drop this denominator. Okay, this is a general trick that we did in the previous example, okay? So when I'm asking for the argmax, I can drop out this denominator. Why can I drop it out? Well, it's the same for every model. The model, which is what I'm maximizing over, is not in that function, the probability of the data. So I can just drop it here, right? The same thing we did with the probability that the windshield was cracked. Okay. All right, great. So this will be the thing we look at, and then I mentioned that there are these two components. Okay, so the first one is the likelihood, and sometimes I will write this as the likelihood of M, the likelihood of the model, and this is the probability of the data given the model. Okay, so that is exactly this term up here, right? So I've written now this probability of the data given the model. I'll often write this as a function called the likelihood. Okay, and you can think of the data as being fixed. When the data is implied in here, I've kind of dropped the dependence on the data. That's often a shorthand that's used here. It's an element of this function, the probability function on the right, but that's often going to be implicit in the problem. So I'm often going to drop that in notation. I'll just talk about the likelihood, and I'll take this over the space of the models. Okay, this is, again, these are the likelihood of A, B, and C, and we had that given to us in the previous example. Yes?
Beneath sigma, are you writing mu or M?
Beneath.
Is that sigma? The n is an element.
Okay, so the n is an element of omega of m. This is the sample space of the models, the space of the models. Yeah. Right, and that's in. That's an in symbol. It looks kind of like an epsilon, but like in LaTeX, this symbol is written as /in. Okay, and you know, there's some mathematical origins to these things of how they wrote it on the chalkboard or in a piece of paper, and it was formalized when Dan Knuth, a computer scientist, made LaTeX, and this stuff started being kind of written down and formalized, and that's helped really crystallize kind of the notation mathematics. But yeah, so it's LaTeX coding is probably the best, most precise way to describe that. Yeah.
Oh, you actually answered.
Oh, okay, great. Yeah. So yeah, and so if you look up in LaTeX on you can Google like how do I do this, and you can find the coding to the symbols. I'll try and introduce that as we go. It's useful in understanding small distinctions if you're reading papers or if you're trying to write something down carefully. Okay, great. So this is the likelihood, and yeah, and I mentioned and I mentioned that this other guy, yeah, and this guy is often called the prior. Okay, so I'll get back to these a bit. We will, in the discrete case I talked about, I can say the likelihood is actually a probability, but this will be a probability density function later on, and so we won't be able to call it probability later. So I can talk about now this way in intuitive language, but later I'll be using likelihood in place of probability because it's not technically a probability when I have a continuous space of models. Okay. All right. Okay. So let's talk about the space of, yeah. So a question is, what is a model and data, right? You're probably, I'm kind of using this. I had this kind of contrived example about the windshield. We're going to go through a simple example today where the one we're going to go through today is where the model is going to be a point, okay? And it's going to point in general in RD, so a d-dimensional space, which we'll talk about a bit later when we get into the linear algebra section. We'll get language to talk about that. We'll talk about a one-dimensional point just today, but all the math will be the same for a higher dimensional point. Okay, it's going to be that point plus some noise model. So we'll assume it's a point plus some Gaussian noise typically. Okay, so plus some noise, and the data will be a set of often IID, and I'll come back to that points also in RD, in d-dimensional points. Okay, and we're going to find a single point which is most representative of those data elements, right? So we can think of having, this is our data, a bunch of these points. This could be in 2 dimensions, and we want to come up with a single model, right, which is also a point here. If I were to try and represent all these points by a single point, well, that could be a good choice. But it could be any point, right? So the space of the models is going to be any point in RD, or if these are one-dimensional data points and they're all kind of on a line, and the model is also a point on the line. Okay, so we'll work through this in sort of detail. This one may not seem so interesting, but it's really the basis for everything else we'll do. The more interesting ones, which we will see in class over the semester, is linear regression. Okay, so this will be one of the things we talk about. Now, the model M will be is going to be a line in general. We'll talk about R2. We'll talk about it could be a hyperplane in RD, but we'll think about this example in R2. Then I'm going to try and fit this model here, this data by a line instead of by a single point, right? So then this model can be a line here, and I'm going to be kind of measuring the error, kind of the distance from the model by these vertical lines. That last one was not quite right. It should be going straight up here. Okay. So this is what the linear regression. We're looking over the space of lines now. You can imagine this will add some complexity to how we do it. But kind of the setup is the same. We're going to have a continuous space of these models. In clustering, okay, there are various models for clustering, but in this case, and in all these cases, the data are going to end up points in RD, d-dimensional points. We could think of them as 2-dimensional points for now. The model now is going to be a set of K points. Okay, so now I'm going to have my data that looks like this, and I might say K is equal to 3. So the model might be 3 points. Okay, so now I don't just need 1 point to represent it, but I can use 3 different points to represent it here. Okay, and so that's how we're going to model clustering. Okay, we're going to do dimensionality reduction. Okay, and there are a few ways again to model this, but here the model M is going to be a k-dimensional so hyperplane. Okay, what does this mean? It's a little hard to talk about in 2D to distinguish it from the case with regression, but an example model would be a line in 2D with this data points And now instead of measuring the air as the vertical distance, I measure it in the projected, the closest possible points. So the orthogonal projection distance. But in general, we have points in higher dimensions, like think of points in 10 dimensions, and I have a 4-dimensional subspace, and I project onto there. And that's what dimensional reduction will model in that way. Okay, in all these cases, the model is kind of this underlying simple structure we can represent in some way, so parametrically, where it might be, it's easy to think of how you parametrically represent a point. You just the coordinates. A line is not too hard. You can do the slope and the intercept, for instance, and that's what we use, or just all this the slopes with some other trick. Clustering not too hard. This becomes, we'll need to do some linear algebra so we understand how to represent this. But you can represent the models parametrically, and kind of implicitly they have a noise model on top of it. Okay, and I'll define that in this case. There's a fourth case I've run out of, and we'll talk about in the semester. That I've run out of space on the slide for, so I'll just say is the classification problem, and that is where, yeah, let me just say classification. Okay, this one's a little bit different. I'm going to have points in RD again. Okay, except I'm going to have two types of points. These are going to be plus points, and these are going to be minus points, and they're come with this label, this notion of a label, and the model here is going to be some, again, a hyperplane, on one dimension lower than the space the points are in, that's going to separate these points. Okay, and the air in some case here is now measured as the distance to this hyperplane. It could be on the points could be on the wrong side as well, and then those points get a penalty. Okay. Okay, so this is the classification problem. It also will kind of fit. This one will be a little bit different, and we'll save this because it's a little bit different. We'll save it till the end of the semester. But the techniques of doing all this are going to be very, very reminiscent. It's possible to model everything the same way here, but that's not the kind of most common way of doing it. So this hopefully gives you a little bit of a preview. Shouldn't completely understand how where this is going, but the idea of the data are going to be a set of observations we have, which we're going to encode as points. Okay, and then the model will somehow be some object, some structural object that we can represent parametrically, based like the coordinates of the points, right, or the slope and intercept of a line. We need to search over all those models to try and minimize some function described by Bayes' rule, but probably the model given the data. We want to actually maximize that function, or we'll minimize the negative of that function is often the case. Okay. All right. So this kind of a big picture sense. This kind of see where this is going. You should not understand all the details at this point. Okay, so if that's a little bit beyond, that's okay. Knut, yep. All right. Okay, so we're going to talk next about the kind of the core. There's a really important mathematical trick that's going on here, and that's called the log. So likelihood is what we want to consider here. And we're going to do a kind of a mathematical kind of reformulation of what we just saw and to construct something called the log likelihood. And we will, the rest of the class today will be kind of working through this kind of this kind of continuous example, the simplest form of this. Okay. And so we're going to look at this this map estimate, right? Go back here. This map estimate was find the maximum of the model given the data, and we reduce that to maximum of the data given the model times the probability of the model. We're going to start with the log likelihood. So we're going to try and find the arg max of a model from some space of models. Okay, so this will be M star, but we're not going to look at, we're just going to look at the probability of the data given the model here. Right, so this term will just be some likelihood. We're not going to look at the prior. So we're going to assume, so when we look at the likelihood, we can basically assume a uniform prior. So we think that the probability of the model is constant. Okay, and so if we do that, we're going to also be able to drop that out of the expression. Okay, so we'll start with this, and then to the next lecture, we'll come back and we'll put the model back in. Okay, and so we're going to find what's called the maximum likelihood estimate, right? So we're going to start again with arg max m in some space of the models, and I think I'll drop the sample space here. I'll just say arg max over m, right? And this will be the probability of the model given the data. And this is equal to arg max space of models given the probability of the data given the model times the probability of the model divided by the probability of the data here. But I already said the probability of the data does not depend on the model, so we can drop that in the arg max. And if the model is constant here, then it means I can also drop this term here. Okay, so then I can say this is equal to the arg max of the model. Let me just say over the space of the probability of the data given the model, right? Which is equal to arg max the model of this likelihood function. Okay. And so when I just look at this, when the model, probably the model said to be constant, meaning it could mean that I assume they're all equally likely in some sense, or I just don't have any information on that, then I'll do this. And this is called a maximum likelihood estimate, an MLE. Okay, so the map estimate is when I factor in this prior. The MLE is when I don't factor in the prior. I just look at the likelihood. Okay, these in general are not the same thing. The probability of the data given the model and the probability of the model given the data, but we're going to just treat it the same in this case. Okay, so today we're going to look at the simpler form, just the maximum likelihood estimate of a simple example. Okay, the next transformation we're going to do is I'm going to do a I want to say the M star equals arg max of some likelihood of a model. Oh, yeah. Good, great. Yeah, sorry about handwriting. Okay, so we're going to do a M star is the arg max of the likelihood. We're going to do what's called a log transformation to get the log likelihood. Yes. LM is just a shorthand for LM in this case will be the probability of the data given the model. Okay, in this case, when I have discrete data, then that's what it's going to be. When I have continuous space of models, which is what we're going to show in the next example, I cannot write this as a probability. Okay, so I'm going to have to write it as I can write it as a function, a probability density function, and that'll often be used just LM. So that's why I'm trying to sometimes use this notation, LM instead. It's more generally correct, where what I'm going to do next, we want to use it for continuous model space, but I can't use the probability in that sense because it's not technically a probability. Yeah, good question. Yeah, this is confusing all the notation here. So definitely ask if I went through it too fast. Yeah.
I can get why we can understand, assume that probability of data is consistent with the same data, but how can we assume the probability of the model?
Yeah, okay, so this probably the model is known as let me give you an intuitive explanation. So the probability of the model is known as the prior, right? And the idea is this comes from some sort of prior knowledge about the situation. And in general statistical modeling, they often say, oh, I have some prior knowledge about what I think the model should look like. It should, because of some some background knowledge I have about some other data sets other than the one I'm using. So I'm going to start by saying, well, I think this model is more likely. And we'll go through an example tomorrow where we try and put this in, and we'll see how to kind of factor this into the calculations. But what we're saying now is that I don't have any background knowledge. I don't want to assume anything about what was known beforehand. Okay, and so I don't want to say this model is more likely than this other model because I don't know. I want to be entirely dependent on the data. Stuff we won't see in this class so much is this prior. So we'll mostly talk about just these likelihood models within this class, right? There are later class you get to in the data mining class, and they'll add what's called a regularization term, which is actually a prior on the model space. And what that does is it keeps the models from being fooled by outlier data in some way. Right? If there is some weird outlier data, you're like, no, that's not right. You know, I know the model is very unlikely to be in that way, and so I put in a very small prior, and this keeps it from getting fooled by outliers too much. Okay, so that's just a little bit of previewing context, but that's okay. So hopefully that's clear. We'll see a more involved example where we discuss this in the next lecture, but today we'll just be looking at this representation. Okay. And so the trick here is we're going to look at the log likelihood. Okay, so we're going to say this is equal to the arg over the space of the models, arg max of log of L of M. Okay, so a log function, right, looks something like from 0 to infinity, right? And it looks, and important point here is the value 1. Right, and a log function looks something like this, right? It goes off to infinity, it goes down to -0, kind of down here. We're particularly interested in this range between 0 and 1 because we're going to be talking about, although it could be anywhere, talking about these likelihoods, which they're kind of like probabilities, but we know that they're greater or equal to 0. We'll treat 0, the value 0 of the log is -50. It's important that it's monotonic. It's always increasing. Okay, so if I have two likelihoods, right, two likelihood values, right, these L of M1 and L of M2, which one, and I know one is more likely, right, M2 is more likely. If I take the log of that value, I'm going to go up to here. Which one is the log likelihood? Which one is bigger? Of M2. It's always going to preserve, it's a monotonic function. So if the likelihood is bigger, the log likelihood will also be bigger. That means if I want to find the arg max, again, I don't care about the value, just the one that maximizes it. If I do a log transformation, it's still going to give me the maximum value. Okay, so when I'm inside this arg max space, I can put a log in front here. Okay, and I still will get the same best model. Okay, and so it turns out this, and it doesn't matter what the base of the log is. Okay, because the base of the log is something that factors out. They're always monotonic, independent of what the log is, right? So this seems complicated, right? Logs are kind of messy to deal with. As computer scientists, you're used to them, base 2 logs a lot, but kind of mathematically, you often don't think about doing algebra with logs. That's kind of our calculus. If we have to do that, that ends up being kind of messy. Will turn out this will actually be useful and will simplify things. There's this property, really important property, that the log of A times B is equal to the log of A plus the log of B. Okay, and we're going to assume independent kind of, and we're going to assume our likelihood is to form our likelihood LM is going to be from independent observations. Independent observations, so it's going to be kind of be like the probability of x1 times the probability of x2 times the probability of xn. Okay, so the likelihood will somehow be a product of things because of independence. Okay, so this we get from independence. We're going to have a bunch of observations, and it's going to be a big joint likelihood. And if observations are independent from each other, that means the joint likelihood factors, and it's the product of all the individual observations. So I'm going to write the likelihood as a product here. Okay, I'm going to end up writing it this way. And inside of a log, what happens to the product? Right, well, let me call this P1, P2 up to Pn. Okay, so what's going to happen to the log likelihood now? The log likelihood of, this is going to be log of the product. This is like a sum symbol. If you've seen like this sigma thing that looks like a sum, if I do a big pi, it's actually called /prod in LaTeX. It's a product of a bunch of elements of over pi, right? So my log likelihood is going to look like this, but that means that I can factor it, right? So I can actually factor this out, and it's going to look like a sum of the log of each of these pi's. Okay, so this is a product symbol. This is a sum. Okay, and it's slash, in LaTeX is /prod and /sum. I guess in old times it used to be a big pi and a big sigma, the Greek symbols, but now they have their own separate representations. Okay, so I'm going to be able to return a product that I want to study into a sum, and the sums are going to be nicer to work with. And it turns out the log will do an extra trick, simplify something else. But let's get into the actual detail example that we're going to go into now. Okay, so this is the log likelihood trick. I mean, it allows me to turn a likelihood determined by a bunch of independent observations that can be written as a product into a sum of the effects of those observations. Okay. Okay, let's see. Let's go into this example. Great, we've got about 17 minutes left, and I think we'll go through it, but we'll kind of redo it again in the next lecture. So we'll just kind of work through the mechanics, and you'll probably might need to see it twice anyways. Okay, so our data in this example is going to be a set of points. This is the data set of points in R1. And in this example, we'll say that these points are 1, 3, 12, 5, and 9. Okay, and we're going to say that these are independent observations. Independent. Okay, there's going to be independent observations of some phenomena we're trying to model. Okay, and our model, we're going to say model is going to be, and I'll use uppercase M here, this model is going to be a point in R, plus so normal noise. Okay, so this normal noise means that there's some, and this normal noise function will be important. So we're going to say particular that there's some normal noise model, which is going to have a, and we will write this as it's going to have a mean of m, which we don't know what m is yet, and a standard deviation of 2, right? And yeah, so this will be, and I can apply this on a point x. This will be x1, x2, x3, x4, x5. I can apply this on a point x, and I will write this as a function g of x. It's a little simpler. And this was going to be equal to the normal distribution with the standard deviation of 2 is going to be 8 pi, so 1 over square root 8 pi times the exponent. Let me write this on the next line here. Okay, so it's going to be equal to 1 over square root of 8 pi times the exponent of negative 1/8. Remember, that was over 2 sigma squared of m minus x squared. Okay, so this will be our noise model. So we're going to assume, what is this going to look like? We're going to have data down here, and this will be x1. It's at a point 1, a point at 3, a point at 12, a point at 9, and a point at 5, right? So these are the data point observations we have. We're assuming there's some model, and I'm going to choose, let's say that if the model was here, I don't know where the best model is, and I want to optimize over all models. But if I chose this model, there's some Gaussian noise or normal noise model with the standard deviation of 2, which is going to have a probability density function that looks like this. Okay, and so I can measure this function at 12 with this choice of model, maybe that's at a point 10, as being at a certain height here, right? That gives me a value. 9 gives me a value here, and 5, 3, and 1 give me very small values. Okay, so this is kind of my model function. So this will be g, maybe gm of x, right? So that's what this blue curve is representing. So this is kind of my model. It's going to be a single point representation where I assume that the data is coming from this point, but there's some Gaussian noise, so I don't get it exact. There's some normal noise distribution around some model point, and I want to find out which model, which choice of the model is the best representation. And again, I have a uniform prior, so I don't assume anything prior about the choice of the model. Okay, so this is kind of the model I'm going to consider here. And so now I want to use this Bayesian framework to find the maximum likelihood estimate. Okay. Okay, so now we need to try and write down and I'm going to use, yeah, so let's say LM here. And remember, this is, and you can think of this as the probability of the data given the model, although we can't really do that because the space of the model is continuous and it's not really a probability here. Okay, it's a PDF, so it's not really a probability, so we have to use this functional form. Okay, but we can think about it as the data, right? The data is these observations in the set D. I'll call this the set D. This is my set D, and I can take the product over the individual likelihoods of each of the data points, right? I know how to write that down. It's the individual likelihoods of a model given this data point, right? I can say the likelihood for a single data point is just represented by this blue function down here for some choice of n. Okay, so I know how to write that down given the assumption of what the model is. Okay. And this is equal to kind of, so if I write this out in the specific form, it'll often take a form that looks like this. By independence of observations, I can write down the joint likelihood as a product of the individual likelihoods. That's what I get from the independence assumption on the observations, and almost all of data analysis, not all of it, but almost all of it, assumes your observations are independent. That's what makes all the mathematics work. So we can actually solve for these things. Okay, remember this was now equal to 1 over square root 8 pi times x of negative 1/8 m minus x squared. Okay? So we've now managed to write down this likelihood function. Okay? Given these observations, we can plug in the values, the 5 values of D. I've written a shorthand for this product over these elements. But we'll actually go in and plug these in about 9 minutes, hopefully. But not till after we've simplified some stuff. We do not want to try and maximize this expression. This expression looks like a mess. Okay, I don't want to try and maximize that. I'm going to use a trick that's going to come up over and over and over again in order to simplify this. And I'm look through the log likelihood. Okay, and let me just go to another slide here. Does everyone have this up? I'm going to rewrite it as the log likelihood. Instead, I'm going to write the natural log. I'm going to use the natural log of L of m. Okay, and this is going to be equal to ln, the natural log of the product over x and d, right, by independence. 8 pi x 1/8 m minus x squared. And all right, this is now the log likelihood. I've turned something messy into something that looks even worse somehow. But I promise you, the next step will start to clean things up. Okay, so I promise what can we do when a log of a product is we can turn this into a sum. Okay, and I'm going to write this as now the sum over x of d. I'll do this in a couple steps here. Log of square root 8 pi x of 1/8 m minus x. Okay, so this looks, maybe this is a little better. The log got pushed inside, but I can do this again, right? Question. It's the natural log, and that will be useful in a second if you can, maybe you can see it coming. But there are two parts here inside of the log, which is again a product. So let me separate these out. Okay, and the first one, I'm going to move the second expression first. This is going to be natural log of x of minus 1/8 m minus x squared. And then the second one does not involve m or d at all. So I can just do the size of d, the number of elements I have. This is the cardinality of the set D, times, I guess, the natural log of 1 over square root 8 pi. Okay? So now I've done, this is starting to look a little bit better. In fact, this last term only depends on the size of the data and then some constant here, and it does not depend on the model. So when I'm doing argmax, I can ignore that term. Okay, so that's good. So I've done something good. I factored out something I'm not going to be able to ignore. Yeah.
Where's the size of
The size of D is because I've taken a sum over this part here, and I broke this into two parts. All the each term, each product here, I can break into two pieces. This piece, and it's the same. And the log, the 1 over square root pi is the same for all of the terms in the sum. So I can just count them. Here, I'll do this in 2 steps.
1 over square root of pi is a scale.
Yeah, and the scalar, but this is for all the elements of D, right? This sum, there are size of D terms of it, and each term has a log of a product, and I can turn that into a sum of 2 terms, and then I put them into 2 different sums. Okay, so then I'm going to do another step simplifying here. Okay, so let me first simplify the second part. Right, each of the term in the sum is the same, so I can just count how many terms I have, which is natural log of 1 over 8 pi. Okay, great. So that's that in 2 steps. What's more important here is that this first step, the natural log of the e to the negative something, right? These cancel also. That's why I chose the natural log. So now I'm going to get a negative 1/8 m minus x squared. Okay, this is kind of the really cool part where the log helps. Aside from the product of the sum, but also this exponent that was in this Gaussian distribution, right? That cancels with the natural log. Those are inverse operations of each other. Okay, so I'm able to simplify that down here. Okay, so now I can write m star equals the arg max over m in of the real numbers of the natural log of this, and this is going to be equal to the arg max of m in the real numbers, right? But so I can recopy this whole thing, but the second term I don't care about, because that's constant for all m. Okay, so this is now the sum, and I'm going to put the negative in front here. The sum of x to the x over the set D. Let's put actually negative 1/8. Pull that out front here of m minus x squared. Okay, and actually the 1/8 isn't going to matter either, right, inside the arg max. And I'm going to actually write this as an arg min instead here. Arg min of, so now I can get rid of the 1/8, and the min gets rid of the negative sign. Now instead of maximizing a negative value, I'm minimizing a positive value. Okay, so now I want to get, so now my goal is to take the minimum of this function of the sum of the squared distances from m. Right, so back to my formulation again. I have these points at 1, 3, 5, 9, and 12. Right, and I want to minimize the sum of these squared distances. Each squared distance now is going to look like a function that is going to be this parabola. Okay, so I'm going to have a parabola which is minimized at each of these points. Right, so these are the individual cost functions associated with each point, and I want to minimize a single point, which is minimizing the sum of all these cost functions. The sum of all these cost functions. It turns out that there's a simple, well-known solution for this, which I'm not going to go through in the lecture, but it's going to be the point that minimizes the sum of the squared distances is exactly going to be the average. Okay, so this is going to be equal to the the average of the set D, right? Okay, so I'm going to say that M star is going to be equal to 1 over the size of D, the sum over X in D of X. Okay, the average is going to be the point that minimizes the sum of squared error. So if you have a bunch of data and you want to model it as coming from a single point with Gaussian noise, it doesn't matter what the standard deviation was. The standard deviation always factored out the arg max. Then the point you should represent is the average of those data points. Okay? Yeah, great.
Let me frame this. So, you see this plot. So what you're saying is that point, the blue M, is the point we're trying to find. It's just going to be all of the numbers.
Yeah, so this is how it looks like for that choice of M of 10, which is not the average. The MLE will end up being the average. Yeah, right. So most of the data analysis will be the averaging of data in some way. We're going to write stuff down and take an average in more and more complicated forms.
So then when you talk about the two people on either side, you're saying not to worry about that Gaussian that you were about to be. If you're looking for the MLE.
Yeah, so this.
That's
Yeah, this one is not going to be the MLE. The MLE is going to be one that's centered so that the product of those red lines is as small as possible.
But you just proved that we were this now.
Yeah, I drew an example which was not the right one, just to get you thinking. Yeah. Yep. Great. Let me turn off live